Oh. Is it Ronglai Zuo?
Yes,
Zuo?
yes. Yeah, Zuo.
Okay, so now we have Ronglai Zuo from Imperial College London. He will be presenting on generating sign language motions via language modeling. So let's give him a quick welcome. Thank you.
Yeah, thank you. Good morning, everyone. I'm Ronglai Zuo. Today, I'm very pleased to share our recent works on generating sign language motions via language modeling. So before diving deep into our works, let me first briefly introduce some preliminaries. So in the domain of sign language generation, which is also called text-to-sign translation, there exist various forms of representations, such as skeletons, RGB videos, and avatars. But skeletons may be somehow too simple to be understood by the deaf people, and RGB videos may suffer from blurriness, and its high dimensionality pose a challenge for video generation models. And our works will use motions as a representation for signs, and they can be rendered as avatars and provide precise details with a low dimensionality. So now the question is how to represent the motions, and we leverage a widely adopted parametric human model called SimpleX. So basically, it consists of multiple groups of parameters, and using these parameters, we can control a template to produce expressive and diverse human motions. But existing sign language data size only provide RGB videos. So now the question becomes how to estimate those parameters from the RGB videos. And in our recent work, we propose a scalable pipeline, which includes multiple pose estimators that are responsible to different body parts, like hand pose and body pose. And the estimations from these pre-trained estimators will serve as an initialization, which are later refined by iterative process with reconstruction laws. And here are several visualizations comparing the raw RGB video frames and our estimated motions. So we can see that our pipeline can accurately reconstruct the motions, and it's robust across different hand shapes and hand poses. Now let me introduce two of our recent works on sign language motion generation. The first one is Sense as Tokens Soak, which has been published in this year's SCCV. Basically, it's a method based on autoregressive language models. The underlying motivation is very straightforward. So we know that sign language is natural language. Then the question is whether we can generate signs in a way similar to generate text. So to achieve this goal, let me first revisit the framework of text generation. And I will use an example of English to Chinese translation. So generally, we will first have a sentence of English, and then we have a text tokenizer to split the English text into a sequence of tokens. And after that, the transformer will predict the Chinese tokens one by one, conditioned on the English tokens. So when it comes to sign generation, the question is how can we have a module to tokenize signs in a similar to the tokenized text? Because sign motions, they are continuous values in the 3D space. So we built this tokenizer based on a technique called vector quantized VE. And the VE consists of an encoder, a decoder, and a codebook. And typically, it's optimized by a reconstruction loss between the input motions and the output motions. And all of the three core components are learnable during this training process. Meanwhile, motivated by the multi-queue feature of sign language, we tokenize signs in a decoupled manner. So that is, we build three parallel VQVEs in which each one is responsible for an individual body part. In this way, we can significantly reduce the vocabulary of signs. So for example, we can use 3 by M tokens to represent M cube signs. Okay, so after obtaining these tokens, then we can fine-tune a language model based over the text tokens and the sign tokens. Generally, the generation process is that we feed the text tokens into the language model encoder, and then the decoder will start from a language identifier and predict the sign tokens iteratively. And finally, these tokens will be fed into the decoders of the tokenizer to reconstruct the final motion outputs. Okay, so due to time limitation, I will briefly introduce the second work. So the previous one is based on autoregressive language model. It's well established and very powerful. It has already successfully been used in current large language models like ChatGPT. But it has also some inherent limitations. So for example, its generation order, its order is fixed as left to right. So that means it can only model the unidirectional context. And this autoregressive manner is also inefficient due to its token-by-token generation process. And in our latest work, we consider a new emerging language modeling paradigm called masked diffusion language model. It models the token distributions in a forward-reverse diffusion process. And in this way, it can model bidirectional context, and it also allows multi-token generation. So it's much more efficient than the conventional autoregressive language model. And we have also successfully adapted into the sign language generation task, and we established new state-of-the-art with reduced latency. And here are several demos of our comparing the ground truth RGB videos, the outputs of the autoregressive solution SOAK, and our latest diffusion-based solution MEDIS.
Sorry, just because they're looking at us whilst we're looking at the screen. Can you start at the beginning again? Is that all right? And then just pause. So just say what that is, and then pause while people look at it.
Okay. Yeah. So this column is ground truth RGB videos from the data sets we use, and the second column is the outputs from our autoregressive language model.
Just 1 second.
Yeah. And the third column is the outputs from our latest work, which is based on masked diffusion language model. Yeah, so we can see it can produce high quality motions and look similar to the ground truth. Okay, so thank you for listening. Please feel free to ask me any questions.
We have time for one question. Oscar?
I have a question. Very interesting work. Thanks. I have a question on the tokens. I have a question on the tokens. Do you account for inter-signer variability in the representation of these tokens, or kind of like how you model the, like when you basically model the sequence as tokens as a language model, right? You may have different representations depending on if a specific signer has, like, I don't know, a different physical appearance, right? That's, yeah. How do you account for that?
So, this is related to the representation we choose. So that is, we choose motions, or we can treat it as a 3D pose. So we do not have the appearance information from the signers. So you can say that they are in when we model. I mean, from the view of the model, they are just 3D poses, not the pixels from RGB videos or images. So yeah, so I think our model is agnostic to the signer identity.
Thank you.
Okay, let's thank Ronglai one more time.
Thank you.
And next we have teacher.
Oh.
Is your surname Kizeltep or Kizeltep?
This is my surname. Teacher Kiziltepe.
Teacher Kizeltep?
Yes, Kiziltepe.
Oh, Kizeltep.
It's